But you can figure out the normalization, and which is useful when you try to do an expansion, just like what we do for sinusoidal function. We can do it for Bessel function in this case. So, we need that. So we need the normalization. So, I mean, this is very simple. So basically, you want to do something like a Fourier series, but now it's a Bessel series. You can say it's a Bessel series, a function of rho that define over 0 to a over, and the most useful case of obviously is F satisfy the boundary condition, like a decay boundary condition. Right? But even if it does not satisfy, just like the Fourier series, it can have a discontinuity at the boundary, and we can still do the series expansion within the range 0 to a. That is still fine. So we want to do a Fourier series, and for using one of these J sub nu. So nu is fixed, but we're summing over this J, the root of this J nu, and the coefficient of C nu J. We sum over J nu is over nu J over A, and actually, yeah. And alpha is the alpha nu sub J, alpha nu J. This is one of the zeros of this J sub nu. Okay. And, okay. This is defined for rho within 0 A. Okay. And this like what we did like this Fourier series, right? Fourier series we use sine and cosine in here, and now we use a Bessel function, a fixed Bessel function with different root in this alpha, right? And now to figure out how you, so once this is just a definition. Say I want to expand f in a series of this Bessel function. So now these are all unknown coefficient, and the way to figure out the unknown coefficient is fairly simple, just like what we did here. You remember what we did for sine. I will figure out the coefficient. What we do now next to figure out to solve the C or the C. What we do? Use the orthogonal of what we just did, right? Of orthogonal condition. How we use that? How we use the orthogonal? Any suggestion? Yeah, integration over F, but not just F. What did we do first? You have this expansion that we want to do, but want to figure out C. And we do an integration, but not just F. F multiplied by F multiplied by this something similar. Right? So it's not. But for real function, assuming F is real, so we don't need the complex conjugate. I mean, generally, if this is complex basis, we need the complex conjugate. But so we multiply F rho by J nu. So you can say you multiply by exactly the same rho alpha J rho A, and also the not just rho, because the integral involves a rho here, so you multiply by another rho and d rho, because that's the weight. So that's the definition of the scalar product with this non-adjoint, non-self-adjoint basis. Okay, but this multiply this one, and then let's get rid of this one. We don't need that now. Now that one is just substitute this one into the F, right? And then now, because we already used J in here, that becomes I. Choose another index and C sub nu I. And then integrate 0 to A rho. Now this one becomes a J nu over nu I rho over A. And multiplied by this one, J nu over nu J rho over A. Right? That is this direct substitution. Now you can apply the orthogonal condition. So this one will be non-zero only if I equals to J, right? So you have a conical delta, right? Because that's what we show over here. Whatever the result, that's the last result. But or the previous one. So when K not equal to K pi, yeah, this one when K not equals to K pi, and you set the Dirac boundary condition, so this is 0, this is 0, so right hand side is 0, and K squared minus K pi squared is not 0, the integral must be 0, right? So the only non-zero is when K equals K pi or alpha nu I equals alpha nu J, or I equals to J, right? So that will give you this one. So this is just this one. Like use of nu I and just copy this one. A square over 2 J nu plus 1 square. And K is the one of these is the alpha nu I or nu or whatever. It doesn't matter. And that is Ka, which is now rho equals to A. And then conical delta I. Okay, and that conical delta just give you the just allow you to sum over it, so that becomes C sub nu J A square over 2 J nu plus 1 square over nu J. C sub nu J is just whatever that is, this integral divided by this coefficient. Right. So this is the normalization constant. So this allows you to write this, solve the unknown coefficient by just doing this integration and then divided by this normalization constant. Okay, and that is that should be your equation 14.48. Okay, so that's how we do the series expansion. And yeah.
Is that 2 or
2? Yeah, this is coming from here. So A squared over 2. Yeah. Yeah. Okay. How much time do we have? 15 minutes. Well, we are about done. We have this Neumann function in next section. You can,
for all real numbers or for different?
any mu in this case is fine. Any j sub mu, and actually there's a restriction. I think nu greater than -1 or something like that for all these. Because you remember this, all these Bessel function has this x over 2 to the minus nu power. So you want this integral to be convergent at at the lower limit. So there's a restriction on nu. I think they work out the nu is greater than -1, right? Otherwise, it would be too singular. But let's because of this maybe just work out this example. Hopefully with the rest of the time. It's actually a long derivation, but hopefully just going through it a little bit faster. This is well, we go through this kind of thing in E&M in more detail, but it's just like a illustration how you use this Bessel series. But this is the problem, like a boundary value problem. It actually is a Laplace equation. So the geometry is you have the cylinder. I think it's called it's from 0 to h. So you have a circular cylinder with a height h, and this is along. I mean the z-axis going through the center of the circle, right? And then the height, this is along the z-axis is right. This is c equals h. Okay, and the circular surface is the radius is whatever. Is the textbook saying a? This radius is a. Okay, just like what we did here. And then the boundary value problem is that the surface, the top surface has a fixed applied voltage V. That could be a function of rho and azimuthal angle phi. And A actually that doesn't depend on, because it's actually fixed at the not A, h fixed on the z equals h, right? And then the problem is to solve for the interior voltage V rho phi h, and the rest of the surface is 0. It's V 0. The side surface is V 0. Okay. All right. So that's to solve it, you can use the separable solution for the Laplace equation, which we did. Actually, we might do the Helmholtz equation, have the extra term, but then you can set the extra term, the coefficient of the extra term, like the case, to be 0. So it basically the same thing. So basically you can now write down because of that, we already went through that. We can write down the solution in the form that we already know what those components are, because this is summing over a bunch of separable solution. So the separable solution has 3 parts. One is the rho part, the radial part. Radial part, we show that it ends up to be a Bessel equation, and the order of Bessel equation actually depends on the azimuthal part. And then the z part is in this case is because it's a Laplace equation. So the 3 constants from the azimuthal part, from the radial part, and then the z part end up to be 0. So you can have 2 positive and 1 negative. So they cannot be all positive and all negative. Remember, we discussed that. And so we have the Bessel equation. Is another way to look at it. You can have 2 coordinate. The solution can be oscillatory in 2 coordinate, and then non-oscillatory in the third one, or oscillate in 1 and then 2 non-oscillate. And so if you choose the Bessel function, which is oscillatory, and the azimuthal angle obviously is oscillatory because of the periodic boundary condition. So you 2 of them, so the c part will be non-oscillation, so they will be exponential function, or sinh or cos. Okay, so in this case, because the lower boundary is 0, so it's much easier to use the sinh function. Okay, so we probably have everything. Now we just write the radial part is j the order end up to be related to the order to the mode of the azimuthal part, which we define as m. And then now because of the psi boundary, psi boundary has to be 0, so we sum over Jm over the root of the Jm Bessel function. So Jm, textbook using J rho over A. So first your J is from 1 to infinity. That's J. So we have, right? So that's the radial part. Now the azimuthal part is just because it's over the whole range of 2 pi angle. So we fix that because of the periodic boundary conditions. So m must be integer. So you actually sum over all integer. And in this case, m is from minus infinity to infinity over all the integer. Okay, so that's fine. And then the z part is a sinh function. And in order that the add up to be 0, it actually turns out to be this is the same alpha mj over a, but now you multiply by z. Right. That when you work out the separable solution, there's a relationship between this argument and that argument, this coefficient and that coefficient. Now in this case, they becomes the same. And now you're expanding using these functions. So you have unknown coefficient. In this case, depends on m, depends on j. Right. And that would be the general solution. Is it okay? So we just write out the solution because we work out the separable solution before. If you're not sure, then you can go through that step, work out the Laplace equation, use the separable solution, work out the separable solution. So a separable solution has the radial part, azimuthal radial factor multiplied by the azimuthal factor, and then the z factor, and then go through the process, and then find out the solution, the equation for each part. So for azimuthal part, obviously is the simple harmonic oscillator, so it's periodic boundary condition, so you get e to the im phi. And for the z part, now instead of simple harmonic oscillator becomes just exponential function solution because that require that all the constant add up to 0, so you cannot have all of them positive, all of them negative, right? And then that the radial part is the most complicated. It turns out to be a Bessel equation of the order the same as the m that you use for the azimuthal one. And then the psi boundary condition require that you choose the Jm with using summing over all the alpha, which are the 0 of this J sub m. Okay, so this is what we do. And now
the hyperbolic function be maximum equal to S.
equal A?
H.
H. Oh, right. Yeah. No. C equal H. The C equal H is the boundary condition. This is this is like the wave number. This is the wave number as the Bessel function. So this is required by the separable solution. Okay. And whatever this H, evaluate H, that's just the part of the coefficient. So now we talk about you can impose the boundary condition. So V rho by H is equals to J from 1. This is equals, not minus 1. 1 to infinity. Minus infinity. Now this becomes just a constant. set z equals to h. So that's part of the coefficient in the sinh of mj over a multiplied by h. And then you have the Bessel function mj over a, and then the sinusoidal function, right? And now we do the same thing. We just did the expansion, and now you have an unknown coefficient, which is this one. The unknown coefficient is this one. And then we have orthogonal basis, orthogonal basis, Jm, and then these are all of orthogonal basis, right? Either Im phi is also orthogonal. Then we figure out now you ask the same question again. You know how to do it, right? How to solve the unknown coefficient? Yeah, yeah, integral, right? Yeah, yeah, multiply this thing again over there. So again, the scalar part involves a rho, so you need to rho phi, and then multiply by Jm. Again, at this stage, you can just copy this one over here. A over a into the I m phi, right? And then you integrate d rho and d phi, right? And d rho is from 0 to a, and d phi can be any periodic period, is 0 to 2 pi, right? So that's the left-hand side, and the right-hand side do the same thing. And when you do that, we already did that. This Jm, I mean, when you put this into here, that you can probably change it to I instead of J, because that you already use J, and for this one you change it like M pi or something like that, right? And then just copy the normalization constant, which is your textbook. I mean, it's just the equation 14.46. So you just work out the A's. You have this. You have first you have this double summation. Now it's from I, from 1 to infinity. You sum of m pi minus infinity to infinity, and then the coefficient will be Cm pi I sinh over m pi I. This yeah, we need that actually, over m pi I h over a. That's the coefficient. And now the integration for the Bessel function part will give you the a squared over 2 Bessel function Jm plus 1 over m pi I squared. And then you have this the normalization for the exponential function. You know that, right? You know that, right? So because m equals to m pi will give you integrating from 0 to 2 pi d phi will give you 2 pi, right? Yeah. Normalization for the exponential function or sinusoidal function is 2 pi, and then you have delta ij delta m pi. Right? And basically that just these two means that you get rid of the summation, change m equals to m pi, I equals to j. With that will give you the whatever that involving this coefficient, and then you just divide everything, you get yourself a C sub m mj. Okay, so that should be your the equation. Finally, your equation in the textbook 14.56. That should be the same. Okay.